This video is for ELEC 1510 Logic Design. This is Lecture 23, Video 2 on Random Access Memory Circuitry, corresponding to textbook section 7.3. In the last lecture video, we talked about how RAM stores bits at certain addresses. So let's actually talk about the circuitry that's used now to do that. Let's look first at the structure of a RAM cell that's used to store 1 bit. We want this cell to have an input so that we can input a bit to store it there, an output so that we can read that bit, a select line to turn on this cell, to basically select this cell as the one that we either want to read from or write to, and then a read-write line that selects either the read operation or the write operation. So now translating that operation into circuitry, the circuit looks like this. We have an input line, a select line, an output line, and a read-write line. There's an SR latch right here, and it's basically going to operate like a D flip-flop, but a D flip-flop with some extra functionality. So we want to first figure out what the S function is based on these lines, what the R function is, and what the output function is. The S operation is going to be the select line and read-write prime and the input. And so the AND operation comes from this gate right here. The R line is going to be select and read-write prime and input prime. The output is going to be select and read-write and Q, the output from the flip-flop. So let's analyze the operation of the RAM cell. When the select line is a 0, SR and out are all going to be 0. For an SR latch, when both of the inputs are a 0, it just maintains its current state. So nothing's going to change. The output will be a 0. This means that the cell isn't selected. When read-write is a 0, the output is going to be a 0, and S and R are going to be input and input prime, respectively. That makes them act like a D latch and makes it store whatever the bit is on the input line. The output then is just 0. When the read-write line is a 1, S and R are going to be 0 again, which means that the latch just stores the value that it previously had, and the output is going to be Q. So that means that we're operating in the read operation. So this is how, basically, this cell is going to act like a D flip-flop with some extra functionality. You can turn off all of the functionality with the select line, and then you can use the read-write line to select between the read and the write operations. In this slide, we can see a 4x4 RAM memory unit. Now, the little squares labeled BC, that means bit cell, and that is the cell that we demonstrated in the previous slide that can store 1 bit and has the select line, the read-write line, the input, and the output. Okay, so we also have an address decoder right here. That is just a simple 2x4 decoder because we only have a 4x4 memory unit, so we only have 4 addresses that we can pick from. So we have address inputs. Those can go from 0, 0 up to 1, 1. Memory enable, that would just enable the decoder. And then a read-write line. We have input data up here and output data down here. So what's going to happen, basically, is let's say I input 0, 0 into the address inputs. Now, the decoder is going to output a 1 on this line and zeros on all of these lines, which means that these 4 bit cells are selected. Their select lines are turned on. Let's now say that I put a 1 onto the read-write line, which puts it into the read mode. So that would send a 1 to basically every bit cell in this whole array, except the only ones that are turned on with their select lines are the 4 up at the very top. So even though technically all of them have the read operation, the only ones that are turned on are at the very top. Now the input data doesn't go anywhere because the read operation makes sure that that doesn't reach the latch. And now the data is taken from the output lines and read out to the output data. Now there's an interesting way of diagramming this using an AND gate basically with an indefinite number of inputs. So when you see an AND gate here that's connected to multiple lines, that basically means that it has all 4 lines, in this case, connected to the input of the OR gate, even though we're only showing one input and it branches out to all possible bit cells. That makes this expandable into an arbitrary number of bit cells. This could be a 64 by 64 memory unit. We would still only draw one OR gate for the output, even though that OR gate would presumably have 64 inputs. So this is the basic structure of a simple memory unit and how you would design the address decoding in order to access different words in the memory. Let's say that now we scale up that memory unit to have 1K words. Well, for 1K words, we would need a very, very large decoder. We would need a 10 by 1024 decoder. That's a pretty difficult thing to design and would take up a lot of space. So instead of doing the decoding that way, we use something called coincident decoding, which is where the memory words are stored in a 2-dimensional array. So we have, for a binary address for a word of memory, an X and a Y component that are each 5 bits. We have a 5 by 32 decoder for the first 5 bits and a 5 by 32 decoder for the second 5 bits. 5 by 32 decoders are much easier to design than 10 by 1024 decoders. And so what happens now is, let's say I input all 0, 0, 0, 0, 0, 0 into the X decoder. That means that this whole row is selected. And then let's say I input 0, 0, 0, 0, 0 into the Y decoder, selecting this column. Well, at the point that those cross, that is the memory word that I'm going to be selecting. So they cross right here, which means that the select line for the bit cells in that 10-bit word are going to be turned on. The way that you would accomplish this is by having the X and Y lines go into an AND gate that then selects those bit cells. So in the previous slide, we had shown what was essentially a 1-dimensional memory array, but that's pretty inefficient, and so this coincident decoding, making a 2-dimensional memory array, is much more efficient. So now let's say that I'm even more space constrained and I need to make the implementation of the address decoder even more efficient. So let's say now that I'm working with 16-bit addresses and I'm going to break those down into an 8-bit row register, so that would be like X from the previous slide, and an 8-bit column register, that would be like Y from the previous slide. I'm going to only input 8 bits at a time, and what I'm going to do is input them in series. So first, I would input an 8-bit address here for, say, the rows. Then I would put a 0 on the row select line and a 1 on the column select line, meaning that there's no decoding going on here for the column, but there is decoding going on for the row. So now a row is going to be selected. Then I switch to inputting the 8 bits for the column. I input a 1 on the row select line to turn it off, and I input a 0 on the column select line to turn it on. Now there's no information going to the row select, but there is information going to the column select, and that way I can input the data in a serial way and save even more space to select the memory word that I want to read from or write to. So a lot of computer science and computer engineering is designing systems like these that make the read and write operations simple, fast, and space efficient. So if you're interested in computer engineering, this is the very beginning of what you can do in computer engineering to make computers faster and more efficient.